Okay, so remember we used real data to calculate the returns to education. So we learned if you attend school one more year, then the hourly wage increases a little bit. So using that example, let's see if you can calculate the OLS using the simple formula here, right? Remember this formula. And from the data, I calculated the mean and variance for you. The education has an average of 13.1 years, and the variance of education is 6.36. And the hourly wage is $7.77 per hour, and its variance is 33. Covariance is calculated as 4.72. Can you calculate from this information, from this basic information, can you calculate the OLS estimator for the slope, right? Okay, if you did the algebra, I'll show you the answer. The answer is pretty simple. Just the slope is covariance divided by the variance of independent variable, explanatory variable. Here it is x, it is education, right? So just plug in the variance of education, covariance. Then the answer is 0.742, which means like for additional year of education, your hourly wage has an increase of $0.742 per hour. And then now you learned the slope. Then what is the estimator for the intercept? Right? Remember this formula. Also use this information. Try to calculate the intercept. Okay, if you have done, we'll show you the answer. It is minus 1.951. Just plug in the average of y, average of x, and the calculated slope. It's pretty straightforward, right? And then compare the result with Excel result. There is a difference. The difference is coming from rounding errors in here and here and here. So rounding errors happen all the time. So yeah, the difference is rounding errors. Like if you use more like accurate numbers, then the answer will be even more accurate, right? The next thing we are going to study is different sum of squares. Earlier we learned sum of squared errors like this. It is errors squared sum. Epsilon squared, epsilon, which is residual, epsilon hat, residuals squared sum. So this measures the size of the error in prediction, or right, how much we could not explain. And using a similar idea, you may calculate regression sum of squares. What it is, this is comparing the predicted value, fitted value, and just the average, right? So given the average, how much the fitted value varies. It's like the variation in the fitted value. It is like if you divide it by n or n minus 1, then it will be a variance. This is called regression sum of squares, and this is explained by this can be interpreted as the variation explained by the regression model, right? You are going to see why it is interpreted this way in a minute. The third sum of squares is total sum of squares. This is literally the variation. So literally this is the numerator of the variance, numerator in the variance, and this measures the total variation in the original data y, right? So total sum of squares is the total variation in y, and then we can prove that. I can show that. I'm not going to show, but one can prove that total sum of squares can be decomposed into sum of squared errors plus regression sum of squares. Regression sum of squares. So because of this, you may explain. So it is clear that total sum of squares is the total variation in the original data, in the original y, and sum of squared errors is the variation of the residuals, the size of the residuals. Therefore, the regression sum of squares can be interpreted as the other among the total variation, except for like other than unexplained variation, you explained. So this is how much you could explain by the model, using the model. By the way, so this abbreviation may be different depending on textbooks. I really hate this. So here's some people call this SSE, some people call this SSR, but others call this SSR, sum of squared residuals, and some people call this estimated sum of squares, so ESS or SSE. So it's super annoying. The worst terminology you could imagine. So there are three things with similar abbreviations, but they sometimes people interchange them. Different textbooks or different programs like use totally different names, so you should be careful. Anyhow, it is a very interesting, by the way, very interesting way to decompose the variation, right? And they are given here. Those are the numbers. Sum of squared, there are three sum of squares. One is regression sum of squares, which is 395, and residual sum of squares, which is 29.46, and total sum of squares, 425. And if you add the first two sum of squares, then you will get the third, exactly the third one. So you can decompose the total sum of squares into regression sum of squares, which is explained, and the residual sum of squares, which is unexplained. That's a very interesting decomposition, and we call this kind of analysis as ANOVA. It is an abbreviation from analysis of variation or analysis of variance, right? ANOVA is the short for analysis of variance. And using that decomposition, we can define a measure of the fit, how much we can explain. So hopefully we hope to have all of the total sum of squares is explained by the model. That will be ideal, right? But it is usually impossible. Usually there are residuals. So then we take this as the ratio. Denominator is total sum of squares, total variation, and numerator is the variation explained by the regression model. So the higher this value is, the better your model explains the data, right? Or so obviously the sum of squares are positives, so it is always between 0 and 1. All right, usually 0 means 0% is explained. 1 means 100% is explained. So in practice, you will see somewhere in between 0 and 1. And its power, explanation power, somehow you may think it as how much the model explains. That explanation power can differ in different applications. Some applications have very high explanation power, but others have very low. It depends on the size of noise in the data, how much randomness the data have. And this is related to the measure of strength of the relationship between x and y. I'm going to explain that maybe soon. So here, let's have a look in our result. R square, by the way, it's called, formal name is coefficient of determination, but usually we call this R square. R square is more commonly used. When I talk with another economist, I say it is R square. R square is like 90%, for example. So in our analysis, R square is given here, 0.9307, which means 93.07%. That is R square, and there is adjusted R square, which is not relevant right now. To understand this, we have to extend the model. So we are going to ignore adjusted R square for now. Later, you will learn if you learn more, if you take more courses. So in our example, R square is 93%, which is 93% of variation in hourly wage is explained by education, which is a great deal. A lot of hourly wage can be explained by education, right? It's very powerful. And the remaining unexplained residual is only less than 7%. Really small. The reason why it's called R square is because R is the correlation coefficient between the actual value and the predicted value. Remember, we could compare actual values and predicted values side by side, and then you can calculate. If you understand the predicted values as a new random variable, you may think of their correlation coefficient between the actual y and predicted y. That's that. And if you take square of that, then you will get R square. Now, why do we need to take square? Because R square is based on sum of squares. So everything is squared. So that's also, it's intuitively makes sense, right? So R squared is named after this correlation coefficient squared. And therefore, the higher R square is, the stronger the correlation coefficient between predicted value and the actual value of y is. Here, the correlation coefficient is given above R square, multiple R square, right? Multiple R is, so it is R. It's about 96%, 0.9647, and if you take square of that, you will get R square, which can be also calculated from the ratio between this sum of squares. And if the R squared is 0, that means there is no linear relationship. Correlation coefficient is 0, no linear relationship. The trend line is flat or vertical. And if the R square is 1, which is really impossible in practice, perfectly linear relationship, like as you saw in an earlier slide, all the dots have to be aligned in a perfect straight line, which is impossible. So anyhow, we just learned what these mean, what these three sum of squared mean, and how we use them to calculate correlation coefficient and R squares. And adjusted R square is for like more complicated model, which we'll skip. Excuse me, this is not education example. Oh, excuse me. I explained this as if education explains the returns to the hourly wage 93%, but no. So this result is from the fake data, the example data that I made up, cost and output. So yeah, it's an example data, so it makes sense because the example data is just an example I made up so that it shows nice pattern. But in reality, with real data, R square is only 10%. So 10%, you may think it's too small, but actually not. So think about this. How many factors determine how many factors determine or affect the wage? Not only education, like a lot of different skills and like age, what is the occupation, what is your major, a lot of things come into effect, but one single factor, education, explains 10%. It's reasonable. Still, it is very high, right? It tells you that education is a very powerful determinant of wage, considering how many factors you need to consider in to explain the wage, right? In that sense, it's not bad, but you may not be satisfied with this R squared. That's also possible. Then we need to use more variables. Like as I said, there must be other variables that affect the wage. Then bring them into the data. Then we may include them. Okay, so I'll explain that in the next video. So thank you for watching. See you later.